Okay, good morning to all of you. We have already discussed about the different types of imperfections and defects in my previous chapter, in my previous class, which we had done on the link. I'm going to explain once again about the defects because you had already noted down the important points regarding different types of defects. What is a defect? Anything, any irregular behavior in the crystal, any change in the orderly arrangement of oppositely charged ions in a crystal lattice due to excessive heating or sudden cooling which is produced is known as a defect. So any change from the regular behavior of a crystal which occurs in a crystal due to two important reasons. Number one, by heating becomes very strong during crystallization process, and number two, if the cooling of the crystals is also becomes very fast, these defects which arise in the crystals are called defects. Defects are of two types. You've already noted these down. Defects are of two types: point defects and line defect. If a defect is at a particular place, we call it point defect. If the defect is in the whole line, we call it line defect. Defects, the point defects are divided into three types: stoichiometric, non-stoichiometric defects, and impurity defects. Stoichiometric defects are those in which the ratio of the anion and cation after the defect is produced in the crystal is not changed. Okay, is not changed. Now, stoichiometric defects are further divided into, one by one I am taking. In the beginning, I told you about what is a defect. Number two, how are they classified? They are classified as point defect and line defect. Point defects are defects which are produced at a particular lattice point. Line defects are, if a defect is produced in the whole line, it is called line defect. Point defects are further classified into three types: stoichiometric defects, non-stoichiometric defects, and third one is the impurity defect. Now I am going to discuss the first one, that is the stoichiometric defects. If the ratio between the anion and the cation does not change after the defect is produced, it is known as stoichiometric defect. These stoichiometric defects are of further two types. Number one, vacancy defects, and number two, interstitial defects. What are vacancy defects? Vacancy defects, kai example I told you, that is Schottky's defect. If an anion, what is Schottky's defect? If an anion and simultaneously a cation loses the crystal structure, they go out of the crystal structure, such type of a and two where anion and cation were present, two holes are created or two vacancies are created, such type of a defect is called vacancy defect. Electrical neutrality is not disturbed because an anion and simultaneously a cation has left the crystal site. This was Schottky's defect. So if you are asked what is Schottky's defect, if an anion and simultaneously a cation loses the crystal site and vacancies or holes are created in the crystal structure, they are called Schottky's defect. It is found in potassium chloride, sodium chloride, silver bromide, etc. It is found in those crystals which have got very high coordination number. Now, what is coordination number? You may write down the definition: the total number of spheres which are touching the central sphere. If you remember, 2 dimension में coordination number 4 था. जब हम 2 dimensions में कर रहे थे, 3 dimensions में कर रहे थे, या 2 dimensions में हम hexagonal close packing में कर रहे थे, तो coordination number 6 था, because the central sphere was touching 6 more spheres. So Schottky's defect is found in those crystals where the coordination number is very high, that is, total number of spheres which are attached to the central sphere is large in number. Number two, where the difference between the anion and the cation is not very large. This was Schottky's defect. 2 holes are created. Number 2 is interstitial defect, the example of which is Frenkel's defect. If a cation, because a cation is smaller in size, loses its crystal structure and comes into the interstitial space, a hole is also created, electrical neutrality is not disturbed, density of the crystal remains the same. Important point, density of the crystal remains the same in Frankel's defect because simply a cation has lost its lattice site and come into the interstitial space. Density remains the same. Now let's go back to Schottky's defect. I told you an anion and a cation both leave their crystal structure. So in Schottky's defect the density decreases, but in Frankel's defect the density remains the same. In your CBSE examinations, 1 mark question come, in which of the four defects there is a decrease in the density of the crystal. So your answer should be Schottky's defect. In which defect the density remains the same, and that is Frankel's defect. So in the Frankel's defect, one cation which is smaller in size loses its crystal structure. उस जगह पे एक होल हो जाएगा, एक वैकेंसी क्रिएट हो जाएगी, and it comes into the interstitial size. Density of the crystal does not change. Now it is found in those crystal structures where the coordination number is not very high. In Schottky's defect, the coordination number was very high. In Frankel's defect, the coordination number is not very large, and there is not very large difference, and there is a large difference between the size of anion and cation. If I say differences between Schottky's and Frankel's defect, in Schottky's defect, one anion and one cation simultaneously leave the lattice site. In Frankel's defect, a cation loses its lattice site and comes into the interstitial space. In Schottky's defect, the density decreases. In Frankel's defect, the density does not decrease. In Schottky's defect, it is found in those crystals where coordination number is high. It is found in those crystals where the coordination number is low. Okay. This way, Frankel's and Schottky's defect we have discussed. This was which type of defect? Stoichiometric defect, where the ratio of anion and cation does not change. Next, let us come to non-stoichiometric defects. Non-stoichiometric defects are those in which the ratio of the anion and cation changes. After the defect is produced, the ratio of anion and cation changes. Now, they are classified into 2 types. Number 1, metal excess defect, and number 2, metal deficiency defect. Number 1, metal excess defect, and number 2, metal deficiency defect. In metal excess defect, one metal ion becomes excess and an anion becomes less in size. I gave you the example. We have a sodium chloride crystal and we heat sodium chloride crystal in the presence of sodium vapors. Excess sodium is attached to the side of the crystal. This sodium ionizes. Sodium changes into Na ions and electron. Now from the lattice side, जहाँ बहुत regular arrangement है sodium ions, chloride ions का, one chloride ion from any lattice side diffuses out of the crystal. A hole is created at that place, and the electron which was lost by sodium, जो excess sodium चिपक गया था, जो electron उस sodium ने निकाला, that diffuses inside and occupies the space which was earlier occupied by chloride ion. Now there is a lattice site which is not occupied by chloride ions, but it is now occupied by an electron. Electrical neutrality is not disturbed at all, but excess metal ions have been created. Why? Because chloride ions have become less. Electrical neutrality does not change, but since chloride ions have become less, so there is an excess of metal ions, hence it is known as metal excess defect. The lattice site which was earlier occupied by chloride ions is now occupied by an electron, are known as F centers, capital F, or also known as color centers. They are responsible for production of color in the crystals. Why does sodium chloride crystal appears to be yellow in color? Due to presence of F centers. Why does potassium chloride crystal appears to be violet in color? Why does lithium chloride crystal appears to be pink in color? For these, the answers is due to the presence of F centers due to metal excess defect. This was one way in which we can produce metal excess defect. The other way there are 2 ways to produce metal excess defect. उनमें से एक तरीका, एक मेथड मैंने आपको अभी बताया. सेकेंड मेथड है कि जब हम कोई क्रिस्टल लैटिस है, we heat it strongly. For example, we have zinc oxide crystal. When we heat it strongly, zinc ionizes. What happens? zinc changes into zinc ions and electrons. These excess zinc ions occupy the interstitial spaces. Zinc will lose 2 electrons, change into zinc ions. These zinc ions कहाँ चले गए? These zinc ions occupy the interstitial spaces, and electrons also occupy any other interstitial space. So what has happened? There are excess of zinc ions, and hence this is again metal excess defect. There are two ways to produce a metal excess defect. You heat a zinc oxide crystal, again metal excess defect is produced. You heat a sodium chloride crystal in presence of sodium vapor, again a metal excess defect is produced, but both are produced in a different manner. I hope you have all understood it very well. Notes you have already copied down. Okay, this was about the non-stoichiometric defect. Now let's come to the next important defects. They are impurity defects. An important point which I had not given you then is the word doping. D-O-P-I-N-G. What is doping? The process of addition of impurities to any crystal structure to increase its electrical conductivity is known as doping. What is doping? D-O-P-I-N-G. The process of addition of impurities, you can write down in your copies when you see this video. The process of addition of impurities to the crystals to make it better electrical conductor, to increase its electrical conductivity is known as doping. Now metal impurity defects, how are they created? For example, we have a crystal of cadmium chloride. We have a crystal of, say, sodium chloride. Okay? There are orderly arrangement of sodium ions, chloride ions, sodium ions, chloride ions. I am adding cadmium chloride to it. What will happen? Since cadmium has the valency +2 and sodium has valency +1, 2 sodium ions from 2 different lattice sites will leave the crystal structure. And out of these, any one lattice site gets occupied by a cadmium ion. This is metal deficiency defect, and it is also found in the transition elements. Transition elements means, for example, we have a ferrous oxide crystal. So there are 2 important valencies of iron, ferrous and ferric. Any 2 positions ferrous is removed and one of the positions is occupied by a ferric ion. From any 2 lattice points, ferrous ions are removed and any one position is occupied by a ferric ion. So this is again metal deficiency defect. Another example I can give you, we have a silver chloride crystal, and to this silver chloride crystal, where there are very orderly arrangement of silver ions, chloride ions, silver ions and chloride ions, I add strontium chloride to it. What will happen? 2 silver ions will leave their lattice positions, and any one of this lattice site will occupied by a strontium ion. Hence, this is called metal deficiency defect. Up till now, whatever I was telling you about the impurity defect, these were impurity defects found in ionic crystals. Now in my next video, I am going to tell you about impurity defects found in covalent solids. That will be in my next video.